Good afternoon, everyone. I am Mr. Ish. Thank you for joining me and for watching my videos. We're looking here at this integrating by parts technique and showing you why it is such a versatile technique. You know the formula right here, integral u dv is equal to uv minus integral v du. This latter part being the more important part, or the part where you actually operate on with regards to the integral you have. It's a versatile technique because of the following three reasons. You can use it on a single function or a lone function where f of x could be something like natural log x or those inverse trigonometric functions, and to derive their antiderivatives, and I've shown you that in one of the videos. These type of functions have very interesting antiderivatives. You can use this technique to derive those antiderivatives. Second reason, at any time you have a function and its derivative serving together as the integrand, you can use this technique, though you know you can also use a polynomial substitution technique, but this technique works equally well. Lastly, anytime you have a product of two dissimilar functions for which the polynomial substitution technique would fail, this technique very well picks up the slack. The versatility is very well demonstrated using this example. If you have something which looks like this, b to the power of 2x ln b, you know if you separate everything, you're looking at b to the x ln b times b to the x dx. This here being your integrand. You know within this integrand you have what is an f of x, and then you have a derivative of f of x. Something for which the polynomial substitution technique would work very well, and we can show you u is equal to b to the x. Derivative of this is b to the x ln b dx, and dx is equal to du divided by b to the x ln b. And when you plug these into this integrand, this is what you get. You have b to the x serving as u, you have b to the x ln b, which is your other function, times du or b to the x ln b. These cancel out, and as is usual for the polynomial substitution technique, you always end up with something like that, and then you have u squared over 2 plus c, which translates here to b to the 2x over 2 plus c, because it's b to the x is your u value, and when you hit it with this 2, it's b to the 2x over 2 plus c. This right here is just looking at via the polynomial substitution technique, but the integrating by parts technique can work very well here as well. If, and you know you always start with these three substitutions or these three determinations, you will of course go for this as your u value. U is equal to b to the x. Derivative of that is b to the x ln b dx, and integral of v would be that which remains, which is b to the x ln b. Integral of b to the x ln b dx. And you know the integration of this is not hard. Think about it. What's the integral of b to the x? Integral of b to the x is always b to the x divided by ln b. You'll do exactly here by pushing out the ln b as a coefficient, and you're looking at something like this, which is b to the x divided by ln b times this ln b which is sitting out, and the integral or the v value is b to the x. And now you have everything you need for that formula, u v minus integral v du. What's u? U here is b to the x. V is b to the x minus v b to the x du is all of this right here. B to the x ln b dx. You can break this part together too, b to the 2x. You can break this part together, b to the 2x ln b dx. But what was this all originally equal to? It was originally equal to that, and let's make it equal to that, b to the 2x ln b dx. You can use that special technique, take it on the other side. B to the 2x is equal to 2 integral b to the 2x ln b dx. And then this right here, your original question, is equal to this coming back onto this side, b to the 2x over 2, and then plus c, and you are done. It's done using the integrating by parts technique. So questions like this, which are seemingly hidden and break into the f of x and the derivative of f of x, which you would normally use polynomial substitution technique, you can still use this versatile technique and solve it through. Now, in the remainder of this video, we'll look at three questions which will highlight the versatility and how enjoyable or useful this technique can be. We have cosine x, natural log sine x. These are the product of two dissimilar functions, and you have to proceed with this. You can make the substitution u is equal to ln sine x. It would make sense to do that. Then you know you have to do du, and you have a chain rule come in because you have to find the derivative of this. If you think about the chain rule and run it through your head, you'll have ln u, and then you'll have derivative of sine x, which is cosine x. You'll have 1 over u coming from the derivative of ln u, and then cosine x, and you'll have cosine x divided by sine x. So cosine x over sine x gives me cotan x dx, which is the value from du. V value is here the integral of that which remains from your integrand. Ln sine x was pushed out, so therefore v must be the integral of cosine x, which is just sine x. Now we have everything for this formula right here to plug in. uv minus integral v du. U is natural log sine x. V is sine x. I'll just push that right here at the very beginning. Minus integral v sine x times du cotan x dx. But within this right here we have things which can simplify. Sine times cosine over sine. These cancel out, so all of this right here, sine x cotan x, is equivalent to just cosine x, and you can see that. This right here is one step from completion. Sine x natural log sine x minus integral of cosine x is sine x plus c. You can isolate sine x from here. You can do sine x for your final answer, then you have natural log sine x. This can be absolute value parentheses minus 1 plus c, and here is your final answer. We look at this integral question, it'll prove to be interesting because it's just a single function in there, but it's a composite, and the best technique here is integrating by parts. You have to do a u substitution, du and v determination. U here must be exactly what's present here, which is just a single function, sine ln x, and the derivative of this is going to be a chain rule coming into play over here. Let's put it right here. If a is equal to ln x, then function with regards to a is equal to sine a, and d over dA is sine a, and then dA over dx ln x is equal to cosine a over x. Derivative of ln x is 1 over x, and you have cosine ln x over x. This is equal to your du value with the dx at the end. So cosine ln x over x dx. V is the integral of that which remains, which is just dx, and you get an x value from that. Now we plug everything into the formula uv minus integral v du, and u is sine ln x. V is just x, and I'm putting that at the beginning, minus x, which is v, and du is cosine ln x over x dx. When you look at this, these x's comfortably cancel out, and then you are doing here another round of substitution. In this instance here, you do u is equal to cosine ln x, and then du is the derivative of that. Let b equal ln x, and function with regards to b is equal to cosine b, and you have to do chain rule over here. D over db cosine b, and db over dx ln x. You have minus sine b over x, which is minus sine ln x over x. V is equal to integral of dx, which is what remained from right over here, and that's equal to x. So we have our next round of substitutions available to us. We have u, we have du, which is all of this right here, and we have v. So x sine ln x minus, from here we do the next round, uv minus integral v du. U is cosine ln x, v is x, I'm just putting that at the very beginning, minus integral v du. X du is this right here, minus sine ln x over x dx, and close the parentheses. When we're looking here, it's not hard. The x's cancel out, the minuses cancel out, you get a positive. You can cancel out this minus and make this a positive, and we open up everything. X sine ln x minus x cosine ln x, plus and minus becomes a minus, and we have integral sine ln x dx, exactly what we started with, all of this being equal to the original integrand. You can take this on the other side and combine it. You'll have x sine ln x minus x cosine ln x is equal to 2 integral sine ln x. So this question required 2 rounds of substitution by parts, and it requires you to do this extra technique to bring everything together and then actually solve for this. You take 2 on the other side and you have all of this. But when I'm looking at all of this, right, you have to take 2 on the other side. I can isolate the x first, and I will. And then I'll have sine ln x minus cosine ln x all over 2 plus c. This 2 is this 2 coming over here and dividing with everything. This right here is my final answer. X parentheses sine ln x minus cosine parentheses ln x, close the big parentheses, all divided by 2 plus c, and that's the antiderivative of that function. We end this video with this question, and I promise you this will be an interesting question because of the way the polynomial substitution technique will come into this along with the integrating by parts technique. You have two different functions over there, one of which is a composite, so you have to use integrating by parts. Initially, u is equal to x, du is equal to dx, and that's my first part. Integral for the v value is what remains, secant square 2x dx. But to find the integral of this, I have a composite. Now I have to do a polynomial substitution over here. If a is equal to 2x, dA is equal to 2 dx, dx is equal to dA over 2, and then I play that into over here because I'm still determining the v. I have secant square a dA over 2. I have 1 over 2 secant square a dA, and you know this right here is a very good antiderivative, which is just tan a, right? Secant square x has an antiderivative of tan x, especially when you're doing the integral. So you have tan a over here, you have this 1 over 2 sitting out, and then you have to resubstitute the a, and my v value is 1 over 2 tan. I have everything here that I need. I have my u, I have my du, and I have my v. All of this right here is my v value. So I have to put everything here in uv minus integral v du. U was just an x, v is all of this, 1 over 2 tan 2a, but here I should make it an x because a was a 2x. 2x minus v, 1 over 2 tan 2x and dx. Now we have a composite here, but an integral which is not too hard. We can rewrite everything here as x tan 2x over 2 minus 1 over 2 integral tan 2x dx. This right here is easy to integrate so long as I do another round of polynomial substitution, and I will. If b is equal to 2x, db is equal to 2 dx, and dx is equal to db over 2, and I bring it in here. So this question starts with a integrating by parts technique, followed very quickly by a polynomial substitution technique, now requiring another polynomial substitution technique just to finish it out, and we will. We have x tan 2x over 2 minus 1 over 2 tan b db over 2. This over 2 can combine with this and make it a 1 over 4, and we can easily do the integral of tan b, which you know will bring the natural log secant. What's our final answer with the substitution? Well, this nothing changes here. X tan 2x over 2, I have a minus 1 over 4. Now the antiderivative of tan b is a natural log secant b, but what was b? B was 2x. 2x, close the parentheses, plus c. So here's my final answer. X tan 2x divided by 2, all of it divided by 2 minus 1 over 4, natural log secant 2x, close the absolute value, parentheses, plus c, and that's your answer. So when it comes to integrating by parts type of questions, you can have a variety of combinations show up. As you know, in this question we started with the integrating by parts technique, uv minus integral v du, followed very quickly by polynomial substitution, followed again by another polynomial substitution, and that took us to completion to give us this antiderivative of this function right here, and the question is done. And that's it for this video. Keep in mind this right here is a very versatile technique, uv minus integral v du, for a variety of integral questions that you will see. So this is something you should be very familiar with. Thank you for watching this video. Have a nice day.